In this video, we'll discuss the force on an electric charge which is moving with the velocity in a magnetic field. This is the definition of the equation. So the force is the magnitude of the electric charge, and this could have a plus or minus sign depending if it's like a proton to be plus or electron to be minus, and then the velocity cross the magnetic field. And you can see this is very similar. I kept this old equation here. This is the force of a wire on a wire which has an electric current flowing in it in a magnetic field, and they're very similar. Both have the second term B, beta, the magnetic field, as the second part of the cross product. So those that have units Tesla. This one has length times current. This one has electric charge times velocity. And you can kind of see they just kind of rearranged it because coulombs per second is amps. So that was this, and then you have the meters for the length. So the units all work out, it's identical. So that's why it's very similar and helpful to remember. This one helps remember the other, and there's three terms here, three terms there. Also remembering that this is a cross product. Cross product means that the resultant force is going to be perpendicular to both those two values. So whatever plane contains those two, the force will be perpendicular, and the cross product depends on the minimum included angle, the sine of that angle between those two input vectors to determine the magnitude of the force. And then the Q, we must remember that if this has a positive charge, then there's a plus sign here, and then the right hand rule works just as it is. If this is a minus charged electrical particle, then like an electron, then there'd be this Q would be minus, and so after you did the right hand rule, then the force would actually be in the exact opposite direction. And it's kind of similar to thinking about Q being positive, and I is any current I is defined as the direction of the positive flow of the charges. So that helps you make sense why this directionality works out. We have 4 problems here to test your understanding of what that's telling us. The first one, we'll assume we have a north and a south pole, and we'll assume there's uniform magnetic field between the two in here. And we have three questions. One, I have a negatively charged particle with 0 velocity. This one, I have a negatively charged particle with the velocity vector shown here. This one, I have a positively charged particle with the velocity vector shown here. We'll see those velocity vectors have the exact same magnitude. Question is, what's the magnitude of the force each one at that moment of time on each one of these 3 particles, and what's the directionality, what's the magnitude, and which one has the largest force magnitude, which one has the smallest force magnitude. Second problem, I have into the board, which is showing, I see the fletchings of the arrow going into the board. The magnetic field, we'll assume it's infinitely large, is on the plane of this, is going into the board. I have a minus charged particle, and initially has a velocity vector shown right here. Question is, at this moment of time, what's the force acting on that charge? And then, as in subsequent times, what's the expected path of that particle? This time, I have magnetic field going in this direction to the right. And assume it is infinitely large. It goes infinitely large into the board. So wherever this particle would see, if the particle went in or out of the board, or any direction this way, it would still say that magnetic field going to the right of the same uniform strength. And there's a positive charged particle, initially has a velocity going straight upward. What's the force at this moment of time? And then where's it going to move to, and kind of what's its path going to look like as it goes through space as time progresses. This one is kind of similar to this, but we have the Earth. The Earth actually, it has the north geographic part, and the Earth's tilted, but essentially the Earth has magnetic field. We call this the magnetic north pole, but in reality, if we view it as a magnet like most other magnets, you think this would actually be the south, because the magnetic outside the Earth, the magnetic field path and circles starting from the southern geographic area around. So if you have a compass in your hand and you have if you have a magnet that you held outside here or on the surface of the Earth, the north part of that magnet would be attracted towards the geographic north part of the Earth, which is actually the south magnetic pole, even though we call it magnetic north. So that being understood, now we have a charged particle, for example, a charged particle from the sun with a solar wind, and that's coming and it's coming towards the Earth. It has this velocity initially, and it's assumes it's a positively charged particle in this case. So what's the forces acting on that particle, and what will that particle do? So these are the 4 questions. So pause and solve. For this first problem then, looking at the first particle, it's a minus electrically charged particle. We're told the velocity was 0, and so since the velocity is 0, we know the force is 0. So even though it has a charge and it's in a magnetic field, since the velocity is 0, the magnitude of the force is 0, and therefore it has no directionality as well. Now going to this next problem, I have I've drawn the magnetic field going to the left, going from the North Pole to the South Pole, and we told it was uniform. So I have to the left magnetic field, velocity of this negatively charged particle, we're told is going to the right and slightly upward. And so we know that the velocity and the magnetic field, the complete elements, are not perpendicular to each other. So, but only the perpendicular components contribute to force. So this velocity has a parallel component to the magnetic field is going to the left. There's a parallel component to that going to the right, the velocity, but that doesn't contribute to the force at all. So if this particle, instead of going upward, had a velocity initially going right to the North Pole, this velocity, that velocity times the magnetic field, so this would be, for example, in the I direction and the minus I direction, that force would be 0, so there'd be no force acting on it. It would just keep going at the same velocity. So this parallel component doesn't matter. All that really affects this is this perpendicular component, which is the velocity times the sine of theta, where theta is the smallest angle between the directionality of the magnetic field and the directionality of this velocity. So I draw a small perpendicular velocity going upward here. That's the perpendicular velocity to this magnetic field. So now, what's the magnitude of the force? Well, the force is the magnitude of this charged particle times the magnitude of the velocity times the magnitude of the magnetic field times the sine of theta. Okay, so that's because it's here. So I know that's the magnitude. The question is, what's the directionality? Well, I know the directionality is always going to be perpendicular to this to both of these, the plane where both of these lie in. So the b is in this direction, the velocity in this direction. So we know that's acting actually in the plane of this board. So I know right away my force is in or out of the board for this problem, because it's perpendicular both to the plane that both these vectors lay in. So let's do the cross product. So velocity, point on my fingers in the direction of velocity, this perpendicular term, magnetic field, so I'm parallel, turn my palm towards that direction, bend inward towards the magnetic field, send my thumb out, so that cross product is out. Another way to do it is first finger, the pointer finger, the index finger is my first term in the cross product, velocity. Then bend this one, this the middle finger at 90 degrees from that. That's the second term, magnetic field. Point this in the velocity first. So there's my tangent velocity. Point that at my magnetic field. My thumb now extended outward shows that the cross product is outward. So the cross product is outward, but does that mean the force is outward? Nah. If the particle is positive, it would, but this particle is negatively charged, so therefore the force vector is into the board. It's shown as the circle with the X through it. So my force is into the board. And the force is pretty small magnitude because this velocity component, sine of theta, is pretty small. As compared to this next problem here, I have a positively charged particle, And this time again the component of this velocity sine theta is this perpendicular component is all that contributes to this force. The parallel component doesn't. So there's my velocity sine theta. This time there's a bigger component of that velocity which is perpendicular to the magnetic field. Again, my force is given by this, but this time theta is going to be greater than this time. So this time this force we know is greater than that. Again, magnetic fields are working in this direction. The perpendicular velocity is in this direction. They're both in this plane. So I know a force is going to be in and out of the board. So let's use the right-hand rule. So let's just do this methodology. First term velocity, second term, which is my finger here, my middle finger is the magnetic field. So let's take the velocity, magnetic field there. So that's direction of the velocity, direction of the magnetic field. There's the direction of the cross product. Is that the direction of the force? Well, yes, because I don't have changing the sign, because I did say a positive charge. So therefore, the force isn't indeed, for this case, is out of the board, and this force is greater than this force, which is greater than that force. So that's the solution for this first problem. For the second problem, uniform magnetic field into the board, infinitely large, negatively charged particle, initial velocity here. So the force magnitude is the magnitude of the charge, magnitude of the velocity, it's magnitude of the magnetic force times the sine of the angle between those two. Well, the magnetic field is into the board, the velocity is out, so there's a 90 degree between those two. So the sine of your theta is 90 degrees, so that's 1. So essentially this goes to 1, so it's just the magnitude of those parts. So that's the magnitude. Directionality, we need to use this cross product. So first term is velocity, second term is magnetic field. So line this with velocity, and then line this with magnetic field. This tells me my force on a positively charged particle would be outward, but since this is a negatively charged particle, but this is a negative charged particle, so that cross product just here alone is to the left, but the minus q makes the force be to the right. So at this time initial, the force is to the right. The other way to do the cross product is this way. Turn my palm towards the second one, turn in. There's my cross product to the left, but I have a minus q, so my force is to the right. So this thing has a velocity here initially, before, and then has a force acting here. So it's going to keep. We know about mass and particles moving. There's no force at this moment acting to slow it down, so it's going to keep moving up. But there's a force that's moving this way, so this part's going to still have a velocity component here, but it will start picking up a velocity component moving to the right. So sometime later it could be some position here because it had moved up and would have moved right as a result of this force. So now think about it right here. It's got some velocity component up and some velocity component to the right. So this was this, I had something here and something there. So it's now velocity is this direction. So think of the velocity, my first term is velocity, second term is magnetic field, is still into the board. So there's my velocity magnetic field at point number 2. This cross product is outward, but I have a minus q, so my force 2 is inward. And since magnetic field is going to be the same and my velocity is the same, the magnitude of the force remains the same for these two cases. Okay, so now it's going to keep going. So it has now picked up more force, which is acting actually to slow it down in this direction, but it's also continues to move it to this direction. So it moved to point number 3. So now where's that point number 3? The velocity is tangent to its path. So there's my velocity 3. Okay, and so there's my velocity at point number 3. So velocity cross magnetic field gives me a cross product in this direction, outward, but I have a minus q, so my force is pointing F3 here, perpendicular to the velocity, pointing to the center here. And you can kind of see if I keep going around Now it's come to this, it's going to be even more velocity downward. So like when I go right across from it, it'll have no velocity component to the right or left, but it'll have the same velocity component initially had. The velocity, first term, second term, magnetic field, velocity, magnetic field, says the cross product is to the left, minus q, force to the right. So force is always pointing to the center, and this negatively charged particle will make a circle in the plane of this board, because there's no forces to drive in and out. These forces are always towards the center. It'll make a circle through this magnetic field path. Looking at the third problem now, I'm told magnetic field going to the right. Let's make a coordinate system. We'll make a right-hand coordinate system to help us solve the problem. We'll make x to be the right, y be the up, and z being out of the board. So we always try using the right-hand coordinate system if you can, as we discussed in the right-hand rule video. So magnetic field is to the x direction, and it's infinitely uniform. It's uniform, and it goes in and out of the board as far as it needs to. It is infinitely large. Initial velocity is up in the plus y direction. So what's the magnitude of the force? Well, that's, as always, is going to be magnitude of the electric charge, magnitude of the velocity, magnitude of the magnetic field at that point, and this times the sine of theta. Well, the magnetic field is in this direction. The initial velocity is in that direction. The angle between them is 9 degrees, so theta is going to be sine of theta is going to be 1. So now I know the magnitude, directionality. Well, magnetic field is in this direction. So initial velocity, my first term, is this direction. Magnetic field is in this direction, so it's in this plane. So we know the cross product's going to be perpendicular to that, so it's going to be in or out of the board. We just don't know yet. So let's use our right-hand rule to figure that out. So let's do it with the methodology of the index finger being the first term, and then the beta, the b, the second letter, the second term is this way. So let's point this in the direction of the velocity, point this finger in the direction of the magnetic field. The cross product is now, we're the direction of the thumb, which is in the board. Is that the direction of the force? Yes, it is, because the charge is positive. So we, at that moment of time, the direction of the force is into the board, but it has initial velocity here. So if I have a particle with some mass that has some initial velocity here, and I have a force which is perpendicular to that, well, that force doesn't do anything to slow down its velocity this way, so it's going to still have some velocity component going up, and I have a force term pushing into the board, so that it'll now pick up, accelerate in that direction, and have some velocity now picking up as it goes up here, as it sweeps around, and have some velocity term going in. So at some time later, it will have swept around, kind of going into the board, so we actually be behind the board, but somewhere up higher. Now has a velocity term which is now tangent to its motion. It's going to be still in the YZ plane, but it's going to be going in like that. Still, this is the equation for the magnitude of the force. Question is, what's the directionality? Well, we can use a right-hand rule. So there's my velocity term, first finger. Second term is the magnetic field, so we'll spin that around. Still, they're perpendicular, the velocity in the magnetic field. The thumb is now the cross product direction. It's in the board and slightly downward. So this is the direction that my thumb's pointing. Okay. So that you can kind of see that force is now it's hard to draw, but it's still in the YZ plane, but it's now toward the circle. And as you can see really I have there's my force 2, and I have the same problem I have right here, except in this case I'm going around in this YZ plane, going counterclockwise, and I'll make a circle around here. Okay, here the force will be there, and this velocity will be there, and it'll keep circling around. And it will stay in that plane, making the circle just like this case did. Let's change the problem just to think about it. So let's say at the beginning, not only did I have some y component of velocity, but I had a little bit of initial component in the positive x direction of velocity. Does that change anything? Well, since that velocity is in the same direction as the magnetic field, I'll never pick up a force in this magnetic field direction. So that particle will never have any force pulling it in the direction, but it has initial velocity there, and that velocity will never, there'll be no acceleration, deceleration. So it'll continue, it'll spin around just like before in this counterclockwise direction, but it will kind of precess as it'll make a kind of helix as it keeps doing that spin, but it'll keep that constant velocity in the x direction. And if I would have made that constant velocity in the minus x direction, well, it just would have spun going to the left instead of the right. So that's the solution for this third problem. And we kind of think that's kind of similar to what this particle is. So we have this charged particle approaching the Earth, and now the magnetic field of the Earth is not uniform. It's going to be weaker here, and as you get closer here, where you cross more lines, it's going to be stronger. But let's look at that moment of time. It has some velocity here. All that matters is the velocity component that's perpendicular to the magnetic field. So I said, even though I have some velocity this direction, that's parallel to this, so that doesn't count. So this is my velocity, which is my velocity sine of theta term. So there's some velocity component here perpendicular to the magnetic field. So let's see what that cross product of velocity, first term velocity, so point everything towards velocity. And then the magnetic field is going from the north to the south, so going this direction. So when I do this, I get a turn there. I get a force that's outward for this cross product, positive charge. So I keep that convention. So it's out. The other way to think about it: first term velocity, pointer finger that direction. Next term beta, turn that way. Thumb is the output force, again saying force is out. So the force at that moment of time on that particle is out. Okay, so that's going to start to make it come out of the board. At the same time, it's still going to be having the same velocity here. So it kind of has a velocity and a force component, and so that's kind of make this part come up, and it's going to be coming out of the board. And then as I keep tracking it, it's going to kind of spin, and as the magnetic field gets tighter, gets stronger and stronger as it approaches the pole, it's the radius of this spinning helix gets smaller and smaller as that particle approaches the North Pole here, and gives us the northern lights with the concentration of that particle approaching there.